Hello everyone, I'm Kukanov, and in this video I would like to present our research paper Cost-Sensitive Optimization for Deepfake Detectors. This research paper was accepted at APSIPA 2020. It is done with my co-authors Janne Karttunen, Hannu Sillanpaa, and my supervisor Ville Hautamaki. First, let me introduce what is deepfake. Deepfake is a technique for generating fake or fictional video or image using deep learning approaches. It can be either variational autoencoder approaches or generative adversarial neural networks or any other advanced neural networks. Parts of the original image are replaced with the generated images from the source one, as you can see on the image in the slide. It can be either face swapping, as you can see here as example, or even real-time face and even posture reenactment. But why do we need deepfake detection? The current stage of the advances of deepfake approaches reach the point when it is difficult to detect fakes with bare eyes. Fake videos with videos and audios keep getting better, faster, and easier to create. Deepfakes already were used in fake news, malicious hoaxes, financial fraud, and other purposes. That is why the purpose of this work was to study, design, and develop deepfake detector to prevent use of AI maliciously. In order to train our deepfake detectors, we have been using open source datasets with real samples as well as fake samples. These datasets are Face Forensics++ and Deepfake Timid. This dataset has diverse fake samples as high quality as well as low quality. We also use Deepface Lab for image cropping. In order to evaluate our deepfake detector models, we have collected evaluation dataset, fake samples from YouTube, and real samples we took from VoxCeleb2 dataset. In total, we collected around 200 videos, annotated face swaps. You can download our open dataset by the following link down below. As the baseline methods for deepfake detectors, we use two approaches. First, convolutional neural network, which is mobile net, and we use Keras implementation, and we trained it from scratch. The second approach is recurrent neural network with long short-term memory units, and it was implemented as described in the paper below. We use also pre-trained inception v3 on ImageNet for raw feature extraction, and the input was a sequence of 20 frames into recurrent neural network. As you know, in practice, evaluation datasets are almost never balanced. The number of real samples and fake samples are disbalanced, and misclassification costs are typically asymmetric. It means that the cost of errors on real samples and fake samples are disproportional, and during the optimization we need to take into account cost sensitivity of error measures. And in this work we prefer to optimize performance measure using backpropagation. That's why in this work we propose to use maximal figure of merit objectives with cost-sensitive optimization. More details on maximal figure of merit you may find below in our recent journal paper. First, let me introduce maximal figure of merit framework, its intuition and motivation. Let's consider example of a three-class classification model. We have input feature vector X, we have output vector G with three scores, one for each class. We also have vector of labels Y, 1, 0, 1. And now I describe how we can model score dependency. I call this modeling as units versus zeros. And for current output scores G1, which has red color in this figure, we call it target output. The confusing output is G2 because it has 0 labels, and the target labels has 1 unit label. The new scores we denote as a psi1, and it will be a difference of target and confusing scores. For the next output, G2, which is labeled with 0, we have confusing classes, which are G1 and G3 in this case, because those are labeled with units. That's why the new output scores, psi2, it is a difference between target G2 and the geometrical average of classes G1 and G3. Finally, the output scores G3, which is labeled with unit. Confusing class for G3 is G2, which is labeled with 0. And the new output score psi3 is a difference between G3 and G2. In practice, we notice that a unit versus zeros transformations allow us better class score separation, and that's why the idea was to use this information in our training process. Formally, units versus zeros transformation is a misclassification measure, and it's represented as a difference between target and geometrical average on confusing scores. Misclassification measure implicitly models the class dependency. On top of misclassification measure, we apply a smooth error function, or we call it L-scores. It can be any smooth function. In this case, we use sigmoid function. It squeezes misclassification score in the range of 0 and 1. And also we have to notice that parameters alpha and beta are trained using backpropagation. Later we use these L scores for error counts. As the evaluation measure for our deepfake detector models, we use equal error rate. After training deepfake detectors, we have target and non-target score distributions, and the point is to choose the decision threshold T. For equal error rate, we also construct false alarm and misdetection increasing and decreasing functions, and the equal error rate is defined on the intersection of these functions, intersection of misdetection and false alarm depending on the decision threshold T. Finally, we introduce the core of this work is maximal figure of merit with equal error rate objective, which is cost-sensitive optimization. We calculate smooth L scores using MFOM framework, which we described before, and we calculate these L scores on each mini batch of samples. Then we calculate smooth false alarm and misdetection based on these L scores. Then we construct MFOM equal error rate objective, which is represented as conditional optimization of false alarm and regularization, which is the difference between misdetection and false alarm, and lambda is non-negative Lagrange multiplier. We optimize this objective using backpropagation. Here I show how we train maximal figure of merit equal error rate objective within the neural network. During training phase, we have DNN part and we have MFOM part. So we forward our samples through the neural network, then we get output scores on the output layer, then we calculate misclassification scores and smooth scores, L scores, and then we calculate our objective function. So we train this using backpropagation. During the evaluation, we cut our MFOM part and we have only DNN part, and we forward our samples and we get only output scores G. Here I represent the results of our experiments. First two rows are showing the results of our baseline models, long short-term memory and convolutional neural networks. You may notice that the convolutional neural network dramatically outperforming the long short-term memory. Also, we explore the mean DCF performance measure. This performance measure is conventional in the speaker recognition field, and more details you can find in our paper. The best performance was shown with convolutional neural network and maximum figure of merit with DCF functions. Since our evaluation dataset was collected on YouTube, it has lots of fake videos which are not used during training. The point was to evaluate our models on the unseen deepfakes. Here we have more insight of performance of our models using detection error trade-off curves on development set and on evaluation set. On development set, the best model is convolutional neural network with MFOM trained on DCF. The other tendency you may notice is that maximum figure of merit with equal error rate optimizes only the region around equal error rate, while underperforming the regions outside of equal error rate. This specificity and the optimization of MFOM with multiple operation points I'm planning to investigate in the future. As the conclusion, in this research we proposed MFOM-based objectives for cost-sensitive optimization. We publicly released our dataset with deepfake videos, which we collected from YouTube, and you can find this dataset following this link. In the future, we are planning to investigate robustness of our deepfake models on deepfake videos and expand our MFOM approach on multiple operating points and performance measures such as DET or ROC curves. Thank you all for your attention and stay safe and healthy.